Well, welcome back to the new format for Math 521 lecture discussion. Today I'll be giving you some warm-up for the number 16 notes that are posted online. It's the first of two lectures on the conjugate gradient method. Which is another iterative method for solving linear systems of equations. It's suitable for linear systems where the matrix is symmetric and positive definite, like the discretizations we've had for 1D boundary value problems and elliptic problems in higher dimensions. So things like if the matrix is the stiffness matrix with in 2D with Dirichlet boundary conditions, or the stiffness plus mass matrices in periodic problems. And what I'll show today is again, just some details, leaving the technical stuff to the notes, which you can read through, showing how the method uses subspaces of Rn. Say n is the size of the problem, so the matrix is an n by n matrix. How the method uses subspaces of Rn, which are obtained from the right-hand side, and operations of the matrix A on the right-hand side. Repeated operations by A are fast to compute because we're thinking of A as sparse, or can be applied quickly through fast transform methods. You'll see at the beginning of the notes there's a discussion of the type of problem that this is going to be useful for. And if you think of the finite element method, then subspaces of Rn, well, the solution is coefficients of basis functions in a n-dimensional subspace in function space. So we're looking at building up approximations in a subspace of that Sn, that function subspace that we first started looking at. And the trick is, in general, this is a technique you could do, but you would have to solve an increasingly large system of equations at every step in this process. And the trick is, in this particular case, the way it's set up, it is a very reduced problem that you have to solve at every iteration as you add a new dimension to the approximating subspace. So that's the trick, and I'm going to leave the technical details to the notes, but I'll warm you up a little bit with the discussion that's gonna start soon. I'll write up a few things, I'll scan them in, and I'll talk you through them, and then point out how the details go in the notes. Again, I hope everyone is well and happy. Some of you may be traveling when this is first posted. I hope you get home safely. And for those of you like me stuck in town, the sun is shining. It's not so bad to be stuck at home as long as you got food in the fridge, which I hope you have. Okay, I'll start up on the notes after I write them up and try this new software which I'm using at home today. Okay, best of luck. Okay, so we're going to just have a little bit of introduction to the notes. We're talking about the conjugate gradient method. So we're solving a linear system of equations. Given right-hand side, we're trying to solve this unknown vector u. U is going to be an n-dimensional vector. This is actually the number of unknowns, not the grid resolution n. So this is the number of unknowns, even if this is a higher dimensional problem. And if A is a symmetric positive definite matrix, and you can look in the notes in the first few pages, that means this matrix A defines a discrete inner product and norm that's different from the usual Euclidean inner product and norm. And how you get this new inner product between two vectors of n components is you take the inner product of u and this matrix A times V. So these would be two n component vectors. You take the usual dot product of those two vectors, but one of them is multiplied by A. So this also has, well, this has all the properties of an inner product. And one of which is if you take the A inner product with U and itself, that gives you a well-defined norm. And if you go way back to the beginning of the term, when we talked about optimal approximations of problems in subspaces of function spaces like H1, if you go back and you look at the matrix A, which is the stiffness and mass matrix added together in any dimension, then if you look at this discrete norm of this vector, that's the same thing as the H1 norm of the corresponding function. And what I mean by the corresponding function is I take these vector components, I think of them as coefficients of the basis functions. And these are the basis functions that you need to define the mass and stiffness matrices. Then this norm is the same thing as this continuous H1 norm of a function u that's in a subspace. Okay, and you can go back to our earliest lectures to relook at this and see how that goes. Now we're going to be looking for approximations of this u vector, in a series of subspaces. And the subspaces are called Krylov subspaces. So they are a nested sequence of subspaces that includes the right-hand side function, and then all multiples of f by a up to m times multiplication by a. So if we had this vector and we wanted to get the next subspace, we would just add another direction, which would be a times fm, which would be a m plus 1 times f. And of course, this idea relies on multiplication by a being fast, if this is going to be a useful numerical technique. And so if a is sparse, right, that's fine. But you'll also see there's some spectral discretizations where the discrete Fourier vectors don't exactly diagonalize the matrix A, where you can still multiply by the resulting matrix A quickly, even if it's a full matrix. And so you have to bear that in mind. For this to work, you have to be able to multiply by A quickly, and that can occur in a number of different situations. If we're just looking at the finite element case, then that's where A is a sparse matrix, which is what you get from a finite element discretization. So we're going to look for optimal approximations in this subspace, and that's going to be our iteration, right? So I'm going to have an optimal approximation in this subspace, which is not all of Rn, and then I will slowly increase the dimension. Now, there's a couple of things that can happen, right? Either I just keep going, right? And eventually I'm going to get to K big N. And if that is n dimensional, then I know that my solution lies in there. And then this will not be an approximation. It'll be the exact solution. Next lecture, I'll show you that if this sequence terminates before you get to an n-dimensional subspace, the solution we're looking for is still in that subspace. So the easiest example to think about is if f happens to be an eigenvector of A, then every time you multiply by A, you just get the same direction. And so this is only ever going to be a one-dimensional subspace. But it's easy to see that if that's the case, then U is that eigenvector divided by the eigenvalue. And so it's in there. And for more general cases, it requires a little bit of thought, but as I say, that's going to be the next lecture. The other thing that I guess I should point out is this is not an arbitrarily chosen subspace. It's one that has good approximation properties. I'm going to show you two steps towards the final interesting thing, where the first two steps are things you could do no matter what the sequence of subspaces was, nested subspaces. And I'm going to leave for next, well, okay. So at the end, I'll tell you what's special about this particular space sequence, and the technical details are in the notes. That's something you just have to kind of look through the details. And then next lecture I'll show you the good approximation properties you get from the subspace. Okay, so we're going to look for optimal approximations in the subspace. And this, again, this is the same trick we had right at the beginning of term. If we look for optimal approximations in the sense of minimizing the difference, so we're going to have an optimal approximation to U, not in the Euclidean norm, but in this A norm. And so what that would mean, since we're in this case where there's an inner product, it means that the difference between the solution, the exact solution, and our approximate solution has to be A orthogonal to all of these f values. That means it has to be A orthogonal to the whole subspace. And if that's true, then the difference U minus UM in the A norm is as small as you can make it as picking a vector from that subspace. Okay, now hopefully I'm going to move on to the next page. We'll see what happens. Okay, so here we go. I got the same thing. I want to make the solution, right? I want to make the solution U, which is a element of this subspace with these coefficients. I want to make it A orthogonal to all of the vectors that define the subspace. So I had the A over here in the definition of this A inner product, but because it's symmetric, I can just push it over on this side. And we have the same interesting thing that we had before. Even though we don't know this exact solution U, we can still make it optimal in this norm because A times U is a known quantity. It's this F, okay? So if I roll everything together, you're going to get a system of linear equations for the coefficients of the approximation. It's going to be a little bit like a mass matrix kind of idea, right? I want the right-hand side f. Instead of a basis vector, I've got this element of the set of vectors whose span is the Krylov subspace. Again, a kind of a mass matrixy thing going on. So you can just plug in the U, expand everything out, and this is what you're going to get. Now, this is not what the conjugate gradient method does. Okay, it does compute those coefficients, but it doesn't do it in this manner. In this formulation, there is a in all generality, this would be a dense m plus 1 by m plus 1 linear system that you would have to solve at each iteration m. And to get to iteration m, not only do you have to solve this linear system, but you would have to keep all of the f L values. This is a to the power L times f. You'd have to keep all of those values to be able to form these inner products. Okay? So you don't want to have to do that. So let's take a step forward. Again, this is not exactly what the conjugate gradient method does, but it's getting closer. Let's consider replacing this set of vectors whose span is the Krylov subspace with an A orthonormal set that spans the same subspace. So I'm just going to do Graham-Schmidt on this set of vectors. So I'm going to take the first one and I'm going to make it have unit size in the A norm, right? So I just divide by its size in the A norm. And to work this out, I just have to take the inner product of F0 with A times F0. Taking A times F0, that's not extra work because that's what F1 is. So you just store that for later on. Okay, and then you want to make replace F1 with a vector that has some component in the direction of F1 but is orthogonal to the previous one. Oh, there's a little bit of a typo. This should be the A inner product. Okay, the A inner product down here. So this F1 tilde, this is the vector F, but subtracting off the projection onto the previous direction. So now this F1 tilde will be A orthogonal to Z0. Remember, there's an A inner product here. And then you normalize it. Okay, and so on. This is just the Graham-Schmidt process. And again, these should be A inner products here. So it's the same story as above. If you are going to construct these vectors, you have to keep all of the previous vectors in the sequence to be able to do this. Okay, so let's move on to the next page. So if I'm going to write my approximating vector is a linear combination of these A orthonormal vectors. So these C's are different from the C's before. I'm just running out of letters, okay? Then it's easy to solve, right? You just take a component of A times U in that direction, but A times U is F. Now, okay, I don't want to make things too complicated for you. But basically, what we're doing is replacing the F's by an equivalent sequence whose has the same span, for which this is the identity matrix. Okay, right? Because if we take those D, K, DL, this just gives you the identity matrix, so it's easy to solve. So when you get to a m going to m plus 1, the previous CLs are exactly the same as they were before, so you don't have to solve a system. You just have to do a Gram-Schmidt process. So that's also time intensive, but if you're looking at solving a sequence of linear systems with increasing dimension, this is a slightly more efficient way to do it. Okay, now if you think about it, everything I've talked about up until this point had no information coming from the choice of Krylov subspace. I could have chosen any set of vectors and made a subspace by taking the span of an increasing number of those vectors. I could have taken the standard basis vectors, and this all would have been exactly the same process. So what do you get extra when you use the Krylov subspace instead of some random subspace to do these kind of approximations in? Well, there's two advantages. One is if you look at the next Krylov subspace vector that comes out, okay, it's not exactly FM, but anyway, the next thing that comes out, and you'll see in the notes, it is going to be A orthogonal to all of the previous vectors except the preceding one. And what that means is you can not have to save any of those previous ones, because remember, the C's based on those previous ones, they don't change. And all you have to do is to subtract off the component of the previous one, right, to get the new orthogonal A orthogonal vector. So the technical details of all of that are in the notes. Now you notice the notes ends with just the method and without indicating that there is some optimality in this technique. Okay, so that'll be the next lecture. We'll look at the error bounds coming from not running this algorithm to completion, which in general would be after n steps. But you'll see there's some optimality in the approximating subspaces that you use along the way. So typically conjugate gradient methods are not run for n iterations. You can get very accurate answers in far fewer than from that for the kind of problems that we're looking at. Okay, I'll turn you loose on the notes and we'll be back at this next Tuesday for the second lecture on conjugate gradient methods, where I'll have notes and a little bit of discussion on the error bound that you can derive for these schemes, which involves the condition number of the matrix A, but there's some ways that you can improve even that bound. You'll see at the end of the lecture notes number 16, there's a discussion of a preconditioned conjugate gradient method. Now in the notes that you have so far, there's no indication of why that is helpful. But next lecture, you'll see why that's a good idea. Okay, hope all is well. I know there's a few of you traveling home, and best of luck traveling. And I will, well, I may never see you again at the way this term is going. But I hope all the best for your travels. And if you're staying in Vancouver, it's a beautiful sunny day. I hope you can get out, keeping social distance, and enjoy the sun.